Hi, I'd like to welcome all of you to the Summer Science Saturday. My name's Tim Swindle. I'm the director of the Lunar and Planetary Lab, and it's great to have all of you here. I hope you've gotten to see some of the great exhibits, the artists from town, various things for the families for the youngsters to look at. But we're kind of focusing this year on Mars, in part because this is the 10th anniversary of well, I call it a camera. It's really more of a telescope in orbit around Mars, taking these phenomenal images of the surface of Mars. And who better to talk about that than the head honcho himself? So it's my very great pleasure to introduce Alfred McEwen. He is the principal investigator for HiRISE. Just a couple of things about Alfred. He is a product and a symbol of the state of Arizona higher education system. He has a bachelor's and master's degree from NAU, a PhD from ASU, and is a professor at U of A. So he's kind of gotten the right order too. And he's won numerous honors, that sort of thing. The one I want to highlight, though, is that the American Geophysical Union has a planetary sciences section. The highest award they give for lifetime achievement in planetary sciences is called the Whipple Award, and Alfred was the winner of that award in 2015. So he is one of the very best, and HiRISE is absolutely phenomenal. So without further ado, Alfred McEwen.
Okay, thank you all for coming. And one thing I really like doing at these public events is taking questions, so I want to be sure and have time for that. Something else I really like doing is having too many slides, and it breaks my heart not to show you all 50,000 images. So I'm going to try to get through these quickly and allow plenty of time for questions, okay? So let's see. A quick overview of the Emerald mission, launched in August 2005, cruise to Mars, orbit insertion, aerobraking, planetary science, and relay phase. The main mission was meant to last for 4 years, ending in December 2010. Well, we've kept going for another 7 years, so that's great. Here's the HiRISE telescope being mounted on the spacecraft structure at Lockheed Martin in Denver. You see people for scale. There's a telescope. There's a full-scale model of this in the lobby of the Sonnet building. Here it is, the whole spacecraft in the thermal vacuum chamber. This is HiRISE here. And this sign says, "Remove before flight." And fortunately, they did remove it. I wanted to get a copy of this, and they said they'd give it, and I never got it. Not a copy of the real thing. Here it is in the fairing, being hoisted up to the top of the rocket. And there's launch. And this is the same rocket that launched OSIRIS-REx recently. So we had orbit insertion in March of 2006, and we had a public event right here in this room. Gabby Giffords was there for that event. How many of you were here back in 2006 for that? A few, all right. So the biggest challenge of HiRISE is speed. We are whizzing over the surface, looking straight down at 3.2 kilometers per second. That's about 7,000 miles per hour, imaging pieces of ground about 30 centimeters, about a foot square, from 300 kilometers altitude. And so to scale that down to something we can relate to, that's like imaging sand grains on the road while driving at 125 miles per hour. So the camera is specially designed to be able to image in this manner. The full HiRISE image reprojected looks like this. We have 10 CCD detectors in the black and white coverage, and then an extra 4 that gives us three-color coverage just in a strip down the middle of 20% of the field of view. And here's a little sample of this at full resolution, but we have this level of detail over the whole image. And I always like to show a very recent image. Here's something we acquired just yesterday to let you know we're still operating. It still works. So I'm going to show you some of the greatest hits or my favorite images. And I'm going to start with our own spacecraft on Mars because that's always a popular item. But when we first arrived in the low mapping orbit of Mars, coincidentally, the Opportunity rover had just arrived on the rim of Victoria Crater. And here's a simulation of what the rover looks like. But we imaged it for real from orbit. This is it, and this is the shadow of this mass cam. Then we re-imaged the Mars Pathfinder lander. Some of you may remember that from 1997. And we see the boulder Yogi that's prominent as seen from the imager for Mars Pathfinder. That imager was built here at the University of Arizona, in this building even, by Peter Smith. Also, for Peter Smith, he had another mission called the Phoenix mission, and they'd picked out a landing site before we got there with MRO. So, and I used to rib him, we're going to see boulders, dangerous boulders all over your landing site. Well, it turned out to be true. We imaged the landing site, and there were these boulders, all these boulders about the size of the lander. You hit one of those at the end of the mission. So I sent him a Halloween card for that, but just a few months later, we had found much better landing sites at the right latitude band for them. So it all worked out. and then we did something new here with the Phoenix. As they were descending on the parachute, the Phoenix lander is in there. This is the parachute. You can even see the cords in the full resolution image. We caught it in flight, descending. And they had just released the heat shield, and that was the heat shield in free flight on the way to the ground. And it looks like it's about to enter this crater here, but that's an illusion. It's a very oblique view. It's actually well in front of this crater. Then we imaged it again on the ground, nice and new, without dust on it, and you can see the 2 solar panels. So having done this for Phoenix, then when the Curiosity rover of Mars Science Laboratory came, we had to do it again. Here it is on the parachute. Now, this is a bigger parachute, and we were much closer to it when we imaged it, so it's a sharper image. So this is it before, and then it crashed. But it lowered down the rover safely first, and then the rest of it crashed. As we continued to take pictures of the parachute on the ground, we saw it shift around in the wind. So that was fun, and that kind of explained we had seen the parachute from the Viking 2 lander from 1976, and we were surprised when it be covered with dust. But if it shifts around in the wind, that could kick off the dust. We also managed to find one of the failed landers, maybe 2 of them, including a Russian one. But this one we found for sure. It's the European Space Agency. I apologize for any acronyms that slipped in here. Beagle 2 lander. They let go of this on Christmas Day of 2003 and never heard from it again. Poor thing. And they had no idea what happened to it. What had failed? Had the parachute opened at all? Did it crash? Well, we finally managed to find it, and that's a story in itself. But we saw that there's the parachute separately, the rear cover here, and then the lander with some of the pedals opened even. So apparently much of this worked. The parachute worked. It actually landed successfully. It began to deploy. Then something happened that caused it to not return any data. So ESA tried again recently with the Schiaparelli lander demonstration module, and it crashed. But again, the parachute, here's the parachute and the back shell. And they figured out what might have happened was that the software was, it's always the software. Software was confused when it was like some altitude of 100 meters or something, and thought it had landed when it hadn't, cut the engines, and then free fell down, which might be what happened to Mars Polar Lander in 1999 as well, although we don't know for sure. So in addition to taking single images, we often take 2 images of the surface from different angles so we can get a stereo view and make digital topography like this. And with that, we can do fun things like make oblique views to show you what it would look like from the ground or from the top of a hill or something like that. And as well as mapping the geology from this. And I believe you've been showing these flyover movies, right? So those are all generated from these digital terrain models and really give you a sense of flying over Mars. I wanted to give you also a feel for what we see from above versus what it's like on the ground, and a particularly dramatic example. This is the high-rise image of the full one with the color strip of one of these mounds, light-toned sedimentary layered materials in Ganges Chasm, and a little blow up here of part of this in the color and full resolution. That's what it looks like looking straight down on it. Well, an amateur enthusiast using our digital terrain models made a view, this view here, from the ground. This is what it would look like, and this is without exaggeration. It really is this steep and rugged. And then in May, I was in Honolulu Convention Center and saw this mural of the Ko'olau Mountains and went, wow, that looks similar. They formed totally differently, though. This has always been one of my favorite images. It's an ancient terrain with diverse colors related to diverse minerals. But why this is my favorite is because once I was in this building in JPL, that's the Jet Propulsion Laboratory where they operate this mission and many planetary missions. And this building was kind of a maze, and I had to find a certain conference room. And I'd seen this picture on the wall without any label, but I asked the receptionist, how do I get to whatever room number it was? And she gave me instructions that included, turn left by the painting. Oh, so having my picture confused for a painting, that made my day. And, these, by the way, are not the natural colors of Mars. These are high-rise vision is shifted into the infrared, so it's not natural color to begin with. And it's also typically very low contrast, looking through the dusty air. So we process and enhance the images to best see the diversity of the surface materials. Just another favorite image. This is of a fan in the middle of a basin, which may have been a sub-lake deposition of this material as shown by this diagram here, which is unusual on Mars. This was a candidate landing site, but didn't go forward. Here's a more recent image that I really like. This is just, again, showing the bedrock layers, including some really reddish stuff. It's probably from iron oxides that make it red. And this is just a pit. It might have been a crater initially, an impact crater, but it's been eroded by the wind and so forth. These look like giant tree ferns. But they aren't really. These are actually, they started off as river channels or stream channels or drainage a network. But within the channel, the water either indurated the soil or deposited coarse pebbles or something. And then with wind erosion over billions of years, it stripped away the surrounding materials and left this as high-standing inverted terrain, we call it. How many of you have been to, say, the Columbia River basalts, Columbia River Gorge, and seen the columnar jointing? Yep. Well, we have columnar jointing on Mars, too. This is some remarkably young lava flow on Mars with some unusual features, ring cone structures, we call them. We don't really see anything quite like this on Earth. This is probably related to volatiles producing these features as the lava is moving, draining away from this area. But how volatiles behave in the Martian environment is very different than on Earth and can produce some unusual looking features, as I'll show you more of. So I'm going to back up in the same basic region of Mars. Emily Lakdawalla at the Planetary Society made this nice zoom sequence to give you a sense of scale. So this is the context image of a wide range of Mars here with there's lava up here, crater here, and we're going to just zoom in on part of this and then zoom in 2 more times. So here's that crater again, and just zooming in to see more detail still in the context image. Then we're going to take a piece of this in here, zoom in again. This is now the high-rise image. We can see much more detail. And one more level of zoom, looks like this. And this is the surface of the lava. And now we see these funny spirals. See those? And those are thought to be lava spirals. So as the lava is cooling and shearing between two moving plates, it produces these structures. This was something really interesting that we didn't notice. It required the image in 2008, but a student at ASU actually found this in 2011. So there are still other things waiting to be discovered in the high-rise data. This image shows layered sediments, again looking down on it from above in a crater. But what's really interesting about this area is you can see the very regular spacing of these layers, and then you can see bigger layers with regular spacing. And so this sort of periodic bedding is thought to be related to climate change on Mars, and it's a record of climate change like polar ice, only these are dry sediments. Here's one of the pictures from the book. That's one of my favorites. It's just layered sediments that's eroded, exposing the different layers, but it looks like cubism or abstract art to me. So, here's another Jackson Pollock version of jumbled blocks in Candor Chasm, probably a landslide of sedimentary rocks. We also have glacial features on Mars. Or ancient glacial features. And this is another zoom sequence. Here, just the full context image. You can see the outline of the impact crater here. Then zoom in to part of the area here. See this flow lobe there. Zoom in one more time. Give you, again, a sense of scale here. We have the elephant. This is actually the edge of a lava flow, an inflated lava flow that's elevated. That's an impact crater. And then aeolian features make the scaly skin. So, okay, so I showed you a bunch of pictures that are mostly ancient Mars. That's not changing. I'm going to show one of the surprises of this mission, of high-rise in particular, is how active the surface of Mars really is. Lots of things are changing in front of our eyes, and we're watching it change. So lots of new impacts. There's over 500 of these now, and these are, by new, I mean we have before and after images. There was no craters there, then there are craters. And we can time exactly, time to the month or year when these occurred. Some of these, well, here's just one example of these. And it makes these dark patterns from atmospheric blasts disturbing the dust. Some of these expose bright white material and looks like ice. And we've watched it fade over time, and that's consistent with it being ice, the rate at which it fades given the known temperatures. And the spectrometer for some of the bigger ones have directly detected the features indicating ice. So there's not only ice, but it's remarkably clean ice. This is more than 99% pure ice. That's only less than a meter below the surface. This is at fairly low latitudes, down to like 39 north is the lowest latitude one we found. The Phoenix mission landed at, I think it was 69 north. They wanted to be where they were sure there was shallow ice, so they could dig down into the shallow ice to analyze it. And the mission lasted only a few months because during late summer it got cold, things didn't work anymore. They could have landed actually at a much lower latitude and found ice within reach of the lander, but we didn't know about it then. We see lots of these dust streaks on slopes. These are dust avalanches, and they change over time. We have dust devils, and this one is particularly interesting because of its shape. And this is the swirling, rotating dust devil that creates this cloud as it moves along and gets sheared in the wind. And then this is the shadow of that cloud. And this is about 800 meters high. We thought that was pretty high until we saw this one, which we're only seeing the base of it, here with high rise. But here's a reprojected view from the shadow of the full height of this thing. It's about 20 kilometers. And there's Mount Everest to scale. So if you were on Mars seeing one of these, they would look extremely impressive. And if this ran into your settlement, it would not be like the Martian where it blew everything over. It's actually, given the low density of the Martian air, it would make a lot of dust and get things dirty, but it wouldn't blow over structures. We have lots of interesting looking sand dunes, including these streaming dunes with transitioning from what's called linear dunes to Barchan dunes. And I wish I had a GIF of showing how these are changing over time. They're moving, but I don't. But here's another one of some other dunes. And there's 3 time steps here. So you can see how the dune is moving along. 1, 2, 3. We didn't know if these dunes were active before high-rise got there. There's lots of active processes in the polar region. This is an impact crater that then got frost in it and then was partially sublimated and had wind blowing a streak across the ice, so lots of things going on at once. One of the really interesting things we found were these polar avalanches. This is the edge of the polar ice. This is a thick stack of layers of ice in the polar cap. And this is about a 60-degree slope, very steep slope. And this is a dust cloud from an avalanche off the slope that is still settling. The dust hasn't settled yet when we took this image. And we've discovered that there's a season in very early spring when the sun first hits these steep slopes. There's a season where there's dust avalanches all along here, or dust and frost avalanches. There are active gullies on Mars. These are erosional features in steep slopes. These were seen some time ago, and it was noted they're very young looking, but now we know they are currently forming, and this just shows a change here where the channel changes, and then there's a new channel down here, new deposits. The surprise with these gullies is that we also have determined when they're changing, when they're active. It's in the winter time when there's CO2 frost on the ground, so dry ice is on the ground. That buffers the temperature, way too cold for water. These look like water-carved features, but they're actually being fluid. The sediments are being fluidized by sublimating carbon dioxide frost, which fluidizes it and makes things move down the slope. Here's another funny thing. There are these, what people have called linear gullies, for lack of a better term, and you can see that they're changing over time, and there are pits at the end. This was kind of a mystery, but then we actually saw some ice blocks within these channels, so we think that blocks of ice break off and basically slide down the hill, settle and sublimate and make pits. So that's some of the activity we saw, and then we found another surprising activity that we really weren't expecting. A lot of the activity I just showed you occurs at the coldest times and places on Mars, and it's because of the carbon dioxide. The carbon dioxide in the atmosphere actually condenses out onto the surface. It gets cold enough. That doesn't happen on Earth. It all stays in the atmosphere, unfortunately. And that drives a lot of activity. But this activity is in the very warmest time of the year. There's no CO2. So we call these recurring slope lineae. Terrible name, but it's meant to be descriptive. Steep slopes, they form and grow gradually or incrementally in the warmest season. Then they fade, then they disappear completely. Then the following year, new ones form. So every year, seasonally, new features form. And that seems very much like what you'd expect from seeping small amounts of water that's seeping through the soil down the slope. And there are features like this in Antarctica called water tracks. we're not so sure that's what they are here on Mars. We're still debating what these are, but they certainly are interesting. And then here's a nice, what do I do, Ari? So here's a movie that was put together with some of our images by the wizards at JPL. Here's the crater, give you some context. We zoom in, there's the high-rise image. And then as we fly along, as if we're in a helicopter inside this crater, we go through this sequence of seeing these RSL form and fade on the slope. So these things start up near the bedrock outcrops and flow over this bedrock in small channels, and then the most obvious features are on these bright fans where they deposit whatever they're depositing. And then at one of these sites, we saw something else interesting happen. This new dark streak formed. Here's the RSL, but this is different. It's downhill from it. And it has topography to it. These things are all just markings. Here we can actually see some structure here and topography at the toe, and there's older slumps here that are the same type of thing. We don't understand these yet either. All right, and so then back to the polar regions and the carbon dioxide. So 25% of the atmosphere condenses out onto the surface as CO2 is up to 1 meter thick. That's why the Phoenix lander didn't last through the winter. There was up to 1 meter of CO2 frost that formed on top of it that we think collapsed the solar rays, or at least one of the solar rays, because from our images it looks like that happened. But as this CO2 dry ice sublimates in the spring, it does all this interesting stuff. It doesn't just quietly go away. It builds up pressure in the subsurface and then makes these little jets that come out and make spots and streaks down slopes, and they change over the season. This is the same feature. This is a dune here, actually, frosted dune through a sequence here. And we have lots of fun watching these. Some of these images, though, are pretty puzzling. The Daily Express a few years ago announced trees found on Mars. You see these features are going straight up, and they've got foliage at the top and everything. Doesn't that look like trees or something? It's better to look at the image this way. These are the tops of dunes, and these are steep slopes, and they're flowing down the steep slope of the dune. That's what's really happening. And this right here is actually a little bit of dust that's being kicked up, so something just flowed, and the dust hasn't settled yet when we took this image. There are spiders on Mars. David Bowie was right. These are channels, radiating channels that flow uphill to a central area. Here there's frost in the channels, so they really stand out nicely. But it's from pressurized CO2 gas as it's sublimating that flows uphill to where it vents out. And we've been seeing these features for a long time and thought that's very interesting, and they must still be forming. But it wasn't until quite recently that we actually have seen a sequence of changes, which seems to be the formation of new spiders forming on Mars. So more current activity. And then when you go to the south polar cap, there's a very bright cap of CO2 frost that stays there through the summer. So it's called the residual cap. But it's changing all the time. We call this the happy face because you see the smile there and kind of a nose, and I'm not sure what kind of eyes he has. But here's just a sample of change here over a couple of Mars years. And this is the same scale. The whole pit is getting larger, and the interior pits are also getting larger. And for a while, some people thought that, oh, the CO2 is disappearing, but it's actually getting redeposited in flat areas. We can see that as well. So it's just moving around constantly. And then one year it actually was glowing. You see this bright glow all around it. And we figured out that this is in a year where there was a global dust storm. The dust was settling out, but this CO2 was sublimating away and preventing from the steep scarps and preventing the dust from settling around this margin. That's what we think happened. Oh, we also imaged the moon Phobos and Deimos, the other moon of Mars, in color. And so what's the future of high-rise? Lots of people ask me that question. We have fuel on MRO for another 20 years. But some of the spacecraft systems are getting creaky. The gimbals that move the solar array, the laser for one of the guidance, navigation, control systems. Fortunately, we have redundancy, so we can use the side B. High-rise camera is still working well. We did have, I told you we had 10 of those red CCDs. One of them stopped working back in 2009 or something like that. Fortunately, it was on the edge of the field of view, so instead of having an ugly gap, it's just slightly narrower. And nothing else as bad has happened since then, but there's no way to predict when hardware might fail, except that the chances increase over time. So we might make another decade, probably not 2 more decades. So with that, I allowed plenty of time for questions. So thank you. Go ahead, sir.
What's the composition of the atmosphere on Mars?
So the composition of the atmosphere of Mars, it's 99 or so percent CO2, carbon dioxide. Earth's atmosphere is mostly nitrogen, has significant oxygen. Fortunately for us, with Mars it's mostly CO2, some trace gases. Yeah, follow up on that.
Where are we going?
When are we going to Mars? Well, NASA keeps talking about it. And they've been talking about the 2030s for a long time, but they really aren't taking the steps they need to make that happen, in the opinion of many people. Meanwhile, Elon Musk and SpaceX wants to build a city on Mars and is doing lots of things that are concrete steps towards Mars. He hasn't gone there yet, but he's taking a different approach than the NASA takes. That might be a lower cost approach, and so there's hope that will work out, or maybe that NASA will collaborate with new industries like SpaceX, so something can happen to make this more plausible. Other countries are interested in going to Mars, like China. And China has never sent a mission to Mars, but they have a very ambitious space program. They have sent rovers and landers to the moon. They're soon launching a sample return from the moon. They're planning to launch an orbiter and a lander in 2020. And that the lander has a rover that's going to collect samples, and they're planning sample return some years later. NASA is also planning sample return, but China may beat us. And then, of course, they really are interested in human exploration ultimately. So it's an interesting race right now, and ESA is interested in collaborating with NASA. So is it going to be the government agencies, private industry, or China that's going to get there first, or someone else? Let's see. Did you pick someone, Tim? Okay.
The linear features on Mars, you mentioned resemble water tracks in Antarctica, and how, again, might water be involved in those features on Mars?
Yeah, so where the water comes from in the present Martian environment is the big mystery. Makes it very difficult to understand these as water. Maybe it's groundwater. That's certainly plausible in limited places, but we found more and more of these, including the tops of isolated ridges and peaks. So groundwater coming out of those places doesn't seem plausible. It's also possible to come out of the atmosphere. This is surprising, but it's been demonstrated that there are these salts on Mars that are deliquescent, Sorry for that word. But that means they can absorb water from the atmosphere and liquefy when the conditions of temperature and relative humidity are right. Those salts definitely exist, including perchlorates. Those were first discovered by the Phoenix mission and since been seen in many other experiments. Those definitely exist on Mars, and the temperatures definitely exist to produce liquid droplets out of the atmosphere, but it's tiny amounts of liquid. So how is that enough to make it actually seep down the slope? Maybe it's actually some sort of a dry seepage process, but then it darkens because of deliquescence. We don't know. We don't understand them.
How long is 1 light year?
How long is 1 light year? So if light is traveling through space, it takes it a year to get to a certain distance. That's called a light year. What is the value of a light year in kilometers? 7 trillion miles. Yeah. So 7 trillion miles, that's how fast light can go in a year. And that's not fast enough to get to most of the exoplanets that we'd like to visit.
I had read in the exhibits out there that the high-rise cameras only actually visualized about 2.5% of the surface. Another camera is at the MRO context camera, I guess, has seen everything. 2 questions. What prevents you getting more of imaging on the high-rise camera, and have people actually looked at all the images from the context camera?
Right, so the context camera, it's about 20 times coarser resolution than high-rise, about 5 to 6 meters per pixel. Indeed, with that kind of coverage, it takes a lot less data, and they've covered nearly all of Mars. And high-rise is limited by data volume from the spacecraft back to Earth. The spacecraft has returned more data from another planet by far than any other mission. And yet, when you're imaging little pieces of ground like this, Mars has a lot of surface area. It has about the same surface area as the land area of Earth. And it's just a very huge data volume. We're hopeful that future technology for future missions will enable getting more data back from Mars, and that's being actively worked, in fact. Has anybody looked at all of the context images? No is the short answer, but maybe people have glanced at low-resolution versions in the course of just finding what they want and so forth. Certainly no one has looked at all of the high-rise images at full resolution. I've tried to do it, and I cannot get through. What you have to do is your computer screen is just a tiny piece of the high-rise image. You have to look at multiple screens and scroll along to see all of it at full resolution. But I get about halfway through the image, and then my brain is off somewhere else, and I don't see the rest of it. So I had never looked at a full high-rise image at full resolution.
Early on, you showed a picture of an impact area where the snow was splattered like a ray pattern on the moon. And I was wondering, this gives you some idea of the overburden layer and how thick it was? And how big an area was that, and maybe how big was the impact object?
Right, so if I remember that image, that crater was something like 50 meters diameter, so relatively small, but bigger than the ones we're watching form today. But indeed, we can learn something about the surface materials. The current impacts expose darker material, sometimes brighter material underneath the dusty surface, so we can see that with the impact. Some craters make terrace craters, so instead of being one bowl-shaped crater, it'll go down, there'll be a terrace, and then another bowl. Sometimes there's yet a third bowl. And that's because of contrast in the mechanical properties of the surface material. And in one portion in the northern plains where there's a lot of these, we've pieced together from the sounding radar that upper layer is actually ice-rich. And then it's the base of the ice that makes the first prominent terrace. Go ahead.
Besides, what images are taken?
Great question. So everyone can decide. We have HiWish, where the public can enter image suggestions, and we have a science team that puts in image suggestions. So we have this big database of targets that people would like to image sometime. Then we have science team members that prioritize those, and then we plan 2-week cycles, and we find those that are possible to image, look at the priorities that were given, but we have a lead scientist for each 2-week cycle that says, well, I really want to image this and that, and you have to make them fit together so they don't conflict with other activities. And so we have this multi-tiered process of deciding what to image.
If the technology existed today to go to Mars, there's a bill of reserve for you. Would you climb aboard?
I think someone younger than me probably should go. I've got some students and former students who'd like to volunteer.
If you don't go, I'll take your place.
Okay.
I would risk it.
What type of fuel is on the spacecraft, and how often is it used?
Right. So there's 2 types of fuel. One is the main engine fuel that it uses, for example, for orbit insertion, and it's done all of those major maneuvers, and basically rarely ever uses that anymore. And then there's what's called propellant. It's hydrazine is what's used, and that's a nitrogen compound of some sort, and it's spurt out little jets, and it helps to control the spacecraft in small ways. And that's the fuel that I referred to, saying that we have another 20 years worth. That's the fuel we use to maintain it's in a stable circular orbit, but over time it will drift, and so just to maintain that orbit we use that fuel. And we don't have any more major maneuvers. We're not going to leave Mars and go somewhere else.
Well, speaking to that, so it gets to the end of its life, do you then put it to a higher orbit and not risk it crashing into the surface?
I'm not even sure of the answer to that question, because at one point I think there was a rule that they wanted spacecraft to be boosted to a higher orbit, so that it would take longer before they might crash to the surface, and that was that was considered a planetary protection issue, where we don't want to contaminate Mars with possible spores from Earth that are on the spacecraft. I haven't heard about that lately. I think maybe they've realized that these orbits are stable for a long time without raising them, and you're there getting irradiated for 20 years or so. Spore is probably not viable anyhow. And once they crash through the Martian atmosphere and heat up, that probably takes care of any. They may have decided that that isn't necessary, but at one point in time, I remember that was discussed. The most efficient size, according to theory, is about 100 microns. So a micron is a millionth of a meter. It's very fine-grained sand, finer than typical sand on Earth. That was the theory. Very recently, the Curiosity rover actually visited some active dunes, the Bagnall Dunes, and took images of the sand grains, and they, in fact, average is around 100 microns, so that prediction turned out to be correct. They were surprised, however, by the diversity of the minerals of all those grains they found in the dune. Go ahead.
Any orbital adjustments that could be made to highlight the entire surface, 100% of the surface of Mars, and what areas would be photographed that haven't been photographed yet?
Right. So right now we can image anywhere on the Martian surface. It's a nearly polar orbit, and the spacecraft can point to the side to cover extra areas when we want to cover them, and to cover the polar. There's a little area we never fly over in the polar regions, but we can point the spacecraft to cover those. So we can image anywhere on the surface. We don't have the data volume to actually do so, and so we don't need to change the orbit to see the whole surface. However, we are in a 3 p.m. sun-synchronous orbit. So it's always mid-afternoon when we image, which is a good time to image. But then there are certain areas that are in shadow, and we can actually see in the shadows pretty well, but it would be nice to have a morning orbiter to see the opposite illumination.
What do you think of the idea of putting a satellite that creates an artificial magnetic field at the Mars-Sun L1? And if there was an easy way to start terraforming Mars, would you support that?
I haven't heard that one about creating an artificial magnetic field. I'd have to consult with some engineers on that one. I really don't know. Terraforming Mars, that's an idea that's been around some time. For those of you who aren't familiar with it, what it means is Mars is inhospitable to people today. But in principle, if you could change the atmospheric composition in particular so that we could breathe the air and that the temperatures were warmer, that's called terraforming. It's never been done before. We're changing the climate of this planet by accident in not a good way. I think I think it could be done, but it would be, in geologic time, it would be temporary. Mars is a smaller planet, less gravity. It doesn't have the magnetosphere unless you create one. And so the solar wind is constantly stripping off the atmospheric gases. And so it would not be stable. Maybe it's possible. I just think that's, maybe you build a dome and just change the atmosphere in a smaller area. Go ahead.
Is there more of a fascination about Mars sustaining than there is about the moon?
I think the general public is mostly more interested in Mars than the moon, simply because Mars does have an atmosphere. It's more Earth-like. It has more Earth-like features on it. The moon is seen as very sterile and dry and so forth. But there is considerable interest in the moon as well, depending on who you ask. And the advantage of the moon, of course, is that it's a lot closer. So for sending people somewhere, that's much more practical than Mars. And some people have argued that before we send people to Mars, we really want to test out all these technologies in our backyard. We've got the moon right there. Why aren't we doing that? And the rest of the world is doing that. Right now, the United States isn't, but that may be changing. Yes?
Can high-rise image the moon from Mars?
Yes, I showed you one picture of Phobos, and we have imaged the other moon, Deimos. There's only 2 little moons. However, it's not the same resolution because we're in this low orbit and we point up. Also, we only see one side of these moons orbit, just like our moon, with one side facing the planet. And so we can only image the Mars-facing side of these moons.
Is there a plan, or maybe it's already been done, to do a methodical mapping of the entire surface of Mars?
Well, using high-rise, no, unless we can keep it going another about 500 years, I think, something like that. So we have covered pretty much the whole surface now with the context imager and with other data sets such as thermal imaging from a previous orbiter, a laser altimeter mapping, low resolution. But so Mars is pretty well mapped already. Mapping it at high-rise resolution, that's a tall order in terms of the data volume. But again, with advances in technology, it's not out of the question that that could be done at some point in the future.
The 3D flyover maps or paths made?
How are they made? So once we have the digital topography, you register the image to that very carefully. Then you know XYZ, including altitude. And then with the computer, you reproject it. So what does it look like from this position, this position, this position? You make a whole series of these reprojections. That's a view of how the scene changes as you fly along.
Any evidence of lava tubes or collapsed lava tubes?
Yes. There are pits this has gotten publicity. There are these pits on Mars with very steep, almost vertical walls, some even overhanging a little bit. We don't see lava tubes in the walls of these pits, but they're in the same sort of geologic setting as pits in Hawaii that are like this, and those do have lava tubes intersecting them. So it's thought to be a high likelihood that these lead to lava tubes. There are also one place in particular where we see a roofed over lava channel that's undoubtedly a lava tube. So there's certainly plenty of volcanism on Mars, and there's no reason why there wouldn't be lots of lava tubes. And that's a potential interest for human explorers because you're protected from the radiation inside of a cave like that. Unfortunately, a lot of these volcanic terrains are the least desirable places to go. And other reasons, they're often very dusty, they're often very high in altitude, they're very rough topographically, so it has everything else going against them. We haven't found a lava tube in a place that's otherwise desirable yet on Mars. Go ahead.
Requests for images, what do you see as the focus of people who want new images? What are they most interested in?
There's quite a broad range of interest. Everything from features of geologic interest to, this is my latitude and longitude on Earth image on Mars. And there's one retired school teacher who's put in a huge number of image requests. And what he does is, if anybody's looked at all the CTX images, go back to that question, it's this guy. He looks at the context camera images, and he sees things that look interesting. He goes, well, that's interesting. I wish I could see it at higher resolution, and he puts in a suggestion for a high-rise target there. And we like his suggestions because they're all pretty much always at least interesting images of something. Yes?
You mentioned mineral diversity. What is the most common mineral surface?
So Mars, the rocks are the first order basaltic in composition, and so they contain the same kind of minerals as basalt on Earth, which includes pyroxene, olivine, feldspars, if you're familiar with those minerals. So they're common rock-forming minerals. There are also altered minerals, clays, and hydrated sulfates and things that are of interest for the past water history of Mars. Yes?
What has been most surprising to you about some of the data that you've gotten?
So the most surprising individual thing are these recurring slope lineae, or they're the most troubling in terms of what are these things and trying to understand them. But the whole suite of different activities on Mars, and I think just the sharpness of the images and looking at them and going, I can picture myself